I think you had slightly hardcore wake up this morning, right? So now we're going to sit back and relax. What I want you to do is take a deep breath, close your eyes, imagine this is not a lecture room, it's a concert hall. Okay? There's a great orchestra behind me, right? Imagine it's quiet. Musicians are musicians, they'll fiddle with the instruments, there'll be a little bit of noise. Okay? And then the conductor comes in, everyone's quiet, sit down, lights go down. Conductor walks in, he raises the baton. The music starts, he's quiet. Violins, perhaps. If you like violins. If you hate violins, it's not violins. Violins start playing. Crescendo, the music got louder and louder. You're thinking, sitting back, relaxing. Oh, starting, beautiful. And then the drums. The drums come in. Now listen. Can you hear the shape of the drums? Can you hear if they're round, small drums, big drums, square? Does it make a difference? Does it make a difference? Have you ever heard a drum? It makes a difference, right? Why is it that people pay a lot of money to buy a violin made by Stradivarius? It's just a violin. Got 4 strings, same size, but they pay lots of money for it. Why is it that you don't give that violin to your kid when they learn to play? Because it's too expensive. So what's the difference? Okay, so musical instruments, right? That's not what I'm supposed to talk about. No, okay, sorry. Musical instruments makes a difference, the shape, right? The material, the strings on the violins, everything makes a difference. So can you hear the shape of a drum? Of course you can. And you can because a drum has normal modes. Right? And what you're hearing are these normal modes, some combination of these modes. You know this from your first sort of physics lectures on waves. And so that's what we're going to be talking about, waves. But we're a little bit more ambitious in orchestras. We're going into space, we're going to talk about neutron stars. And so today, what I'm hoping to do is to motivate why in this day and age, when we have supercomputers and things like that, we still need to understand perturbation theory, linearized theory, things like that. I'm going to try to explain to you the context. Then when I'm done, we'll just finish. It takes 5 minutes, we're done. It takes 90 minutes, we're done. If it takes 5 hours, we can just keep on going. Ajith is not going to stop us. We can try. I can take him. Maybe not, actually. I probably can't. I shouldn't say these things when it's recorded, but I have a problem with my mouth just keeps on going. Okay. So the context is not music. That was just a way to get you thinking about what the problem is. The context is seismology. So if I write down the word seismology, then what are you thinking about? I suspect you're thinking the Earth, right? You're thinking earthquakes, right? Maybe. I'm thinking earthquakes because I like disasters, like this lecture will be. Now, I don't know what you know about earthquakes. Probably that was not part of your gravity course. But it's a known fact that from the seismic waves caused by earthquakes, you can map the Earth's interior. You can figure out what the Earth is made of. There's a lot of recent discussion. In fact, I saw a paper this morning about some journal somewhere. I didn't pay much attention. It was a little bit early. But there's a paper this morning about how you can probe the Earth's interior, the solid core, which is kind of small. It's about 1% of the Earth's mass. by waves going through due to seismic events, and how you can figure out that the iron in the Earth's inner core has to be moving around. So we can learn about the interior of the Earth by mapping seismic waves. In fact, in the 1960s, people used this idea to map the different waves that propagate in the Earth's crust and the inner core, or in the core, to figure out what the Earth is kind of, how it works. And they did that by mapping the oscillations on the Earth onto this problem. So how the seismic events trigger waves in the star or in the planet. So I kind of knew this. Everyone knows this, I suppose. And then you might know, because this can be about, I went up, excellent, because I didn't want to shout and I can't. You might have seen, it's kind of funny, if you're interested in gravity and gravitational waves, the gravitational waves can be used to map, not the gravitational wave detectors can be used to map seismology. But in fact, the sensors that you use to make sure that you avoid seismic noise provide precursor signals for earthquakes and things, tsunamis that are about to happen, which means that gravitational wave detectors are good also for the Earth, right? Or earth science, which is something I never thought about, but it's just a byproduct. Something we want to get rid of, the seismic noise, turns out to be the signal that someone else is interested in. It's nice. So I knew that, I guess. What I didn't know was that there are also moonquakes. I'd never heard of that. I just wrote it on the board, so it must be true. So there are moonquakes because the tidal interaction, whoa, thank you, that was maybe a little bit much. Because the tidal interaction between the Earth and the Moon triggers waves in the Moon. And if they get a little bit too strong, the Moon just quakes. So it cracks a bit and it has moonquakes. And you can figure out, if you knew what the oscillations were that triggered by these quakes, what the Moon was made of. So if you go further, I guess you can go to the other planets, right? So let's go to Jupiter, say. Jupiter is nice, it's big. Now, you can use the same idea. The waves in Jupiter, so the seismology, if you want, explains things like the red spot is a wave phenomenon, the surface of Jupiter. But there's also tidal interaction between Jupiter and its moons. That's a big sort of thing that people are trying to track, because we now have observations that allow us to figure out how that works. And the tidal interaction, as I will try to explain to you probably on Wednesday, is associated with seismology. You can frame that problem as a seismology problem. Now, I want to be more ambitious, if I can. I want to go further out. But first, in the solar systems, we're going up in size, right? So the sun is well known to have a huge numbers of oscillation modes that we have observed with things like the SOHO satellite and things like that. So this goes back to the 1960s, 50s again, when people figured out that there was a 5-minute variation in the sun. And now we know thousands of the different oscillations of the sun. There's a whole area, which you're welcome. You can leave the room and go and join that area if you want. It's called helioseismology, where people work to figure out what's inside the sun. So what we've learned is that the sun does not rotate like a solid body. It has differential rotation, where the rotation's rate depends on how deep you go into the sun. So we learned things from trying to figure out these variations in light. For the sun, you can sort of imagine seeing little parts of the surface bobbing up and down in different ways. And you can map that onto some decomposition in, say, spherical harmonics. and you can figure out what these frequencies are. Okay? Now, the same idea then obviously applies to stars. But we can't use helio anymore. We have to have a different name. So this field is called astroseismology. Okay? There are many books and papers and things on this. So the challenge now is, can we see variations in the light or some signal from stars? And you may know that we can, right? We know there are variable stars like the white dwarfs that oscillate radially that we use as part of the cosmic distance ladder. The first step on that ladder is variable stars, right? So clearly we can do this. I'm not that interested in radial oscillations because I'm a gravity person. I demand and crave gravitational waves, and radial oscillations are completely useless. As you know, you need quadrupole deformations to get gravitational waves. So that's not so interesting to me. But non-radial variations in stars has also been observed. In fact, this you may not know, but the astroseismology strategy to try to figure out the oscillations of distant stars is key to the search for exoplanets. Doesn't make any sense, right? Why so? Well, that is so because in the search for an exoplanet, you see some variation because some little planet distorts the star. But you need to be able to characterize the host star. You need to know what kind of star it is to be able to say something about how big the planet is, right? And that you do, that characterization you get from astroseismology. From the oscillation properties of that star, you figure out what kind of star it is, and that tells you, you know, if this is perhaps one day an Earth-like planet. Today, I think we seem to mostly have Jupiters, but anyway. So what I wanted to get to is this is an area of long tradition in earth sciences and astronomy. Okay? So that's not what we're talking about, and I've just wasted a lot of time. This could be a stalling technique. If I could keep on stalling for 90 minutes, then that would be great, right? Then we can have lunch and forget all about it. But this set of lectures is basically about this, but really about neutron stars. So I want to use neutron stars to do seismology, or do the seismology of neutron stars. That's my plan, or my dream, my hope, whatever it is. And so what I'm going to try to get through to you is how we go about this, what the sort of main properties of the problem would be. There's going to be a lot of touching on physics. These lectures are going to be deliciously dirty compared to the other ones, okay? Because we're going to have a lot of physics. Some of it we can do, some of it we can't do. We can talk about it, but maybe not calculate it. So that's one thing we want to do. And I think we'll get to illustrate some aspects of why this is true. In fact, I hope to do that today in words. So now here's the problem. Neutron stars are small. Neutron star is something like 10 kilometers, weighs about 1.5 times as much as the sun. You know all this, right? But it's too small for me. I don't have a telescope that allows me to look at it. Even in the cases where I can see surface emission, I just see some hotspot kind of thing, right? I cannot possibly go in and, like we do in the sun, distinguish little bits of the surface going up and down. It's never, ever, ever, ever going to happen, no matter how much money you give me and how big a telescope we build. It just won't happen. So if I want to do neutron star seismology, I really don't have a choice. I'm going to go to the gravitational wave person and beg, you know, please find ways in which gravitational waves can be detected from neutron star seismology. Okay? So is it possible that that can happen? It hasn't happened yet. Is it possible that it can happen? Well, I think so. I'll give you 3 examples. The main 3 examples, I suppose. So the first one is when the neutron star is born. Neutron star is born in a supernova core collapse, where the core collapses to form a proto-neutron star that then cools. Right? I think there is no chance that this event will be perfectly symmetric. Right? It will have some asymmetry, some waves sloshing about and things happening. Now, we know from numerical simulations that the amplitudes of these oscillations are small, but at some point, if we keep on improving the detector technology, or if a supernova goes off just beyond the moon or something like that's not going to happen, but in the galaxy, this kind of signal would be quite strong. It would be easily detectable with LIGO right now. If a supernova goes off at this moment, we would have the most spectacular information of what happens inside this newly born star from LIGO. And that information is encoded, as we know again from numerical simulations, in some sense, in linear oscillations, the fundamental mode that we will calculate together tomorrow, okay? Or sketch at least a simple version of tomorrow. And we know that from simulations done by lots of people, but in particular, the group of Adam Burrows at Princeton this last year have demonstrated this very clearly. In fact, I went to a talk given by Adam Burrows on these supernova simulations they've done, where they track the star for the first 6 seconds or something like that. And they have a beautiful diagram that I then went away and discovered in my own book of gravitational waves, because I have the same diagram. My book came up before their simulation, so I win. Because the calculation was done in perturbation theory nearly 20 years ago. And the interesting thing is the simulations are now caught up and the results look exactly identical. Which is beautiful. Right? It means we understand what's going on. The next problem is one that's very dear to me. I'll talk about this on Thursday. It's the problem of unstable oscillations, where the star, for some reason, the wave is somehow unstable, so it grows in amplitude. There are many instabilities in stars. For example, the maximum mass discovered by Chandrasekhar in the 1920s is an instability due to the radial oscillations with the star. Those oscillations become unstable and therefore forces the star to collapse. Instabilities of non-radial oscillations lead to things like dynamical instabilities if you've got rapid rotation. And then we have gravitational wave emission that can drive oscillations unstable. And so that's the one I'm going to talk about on Thursday. It's called the Chandrasekhar-Friedmann-Schutz instability. And we're going to derive why that works. And so we see how it could possibly be that emitting waves can. So that instability was discovered in the 1970s. The main work was done. Main paper came out in 1978 that explains how this works. So it's a long, old thing, but there's still work going on this. And there's, of course, been LIGO searches for this kind of thing. So there's some papers on that. So we're going to try to understand how that works. And then finally, we're going to talk a little bit about neutron star binaries. So how there are seismology features in binaries. Okay. So I'm going to try to convince you, because this is my gospel at the moment, that the tide, as I talked about earlier, can be represented as a seismology problem. Okay. So that's what we're going to do. And we're going to do, how does this work? We're going to do the mode tomorrow. We're going to do this on Wednesday and that on Thursday. And then what we do on Friday, we just take a break. On Friday, we're going to do a little bit more how it really works, okay? I'm saving that for Friday, so you're all exhausted. And then we'll hit you with how it really works. I'm just going to make totally fairy tales up until Friday. That's my plan. Okay, so let's talk a little bit about this problem, because we already have some evidence from this, because we've never seen this thing in gravitational waves. We certainly haven't seen this thing in gravity, but we have seen binary neutron stars. So let's talk about (170817), the first binary neutron star in spiral detection. Okay? So how does this fit into this picture? I'm going to do what you say. I'm going to draw a diagram, and it's going to be terrible. We had the conversation about how scientists should never draw diagrams because they're always awful. Apart from Roger Penrose, he draws the most beautiful pictures by hand. And then someone like me comes in and demonstrates why there is a reason I did not do an art degree. But my diagrams look like something drawn by a 2-year-old. So I'm now going to demonstrate this. And now you're primed to appreciate how great this is. So in gravitational waves, we often draw characteristic amplitudes. So that's effectively the amplitude that you see when you do the data analysis. How strong is the signal really? So for a binary, what happens is at low frequencies, the system spends a long time. So you can integrate over that for a long time and you gain in signal to noise. So the signal is weaker because the stars are further apart, but you integrate over for a longer time. So the effective amplitude you get is higher. Okay? And then as you get closer to merger, the frequency, orbital frequency goes up. It spends less time. The amplitude of the signal also goes up, but actually it works out that you lose. So the effective amplitude goes down. So a binary in spiral looks a little bit like this. This is my highly scientific drawing. Okay? In effective amplitude. And then over here somewhere it says crash. It says stars come together. We should do simulations. I should have a movie, but I only show that movie in popular talks. So sorry, if you weren't there yesterday, you lose. But it was beautiful. It had sound and everything, right? Okay. And so now we want to detect this. We need to build a detector, but at low frequencies, we have seismic noise. I talked about that already over here. So the seismic noise kills us. There is no way that we can detect gravitational waves on Earth below something like 1 hertz with LIGO several tens of hertz. It just doesn't happen. And then at high frequencies, well, we're killed by photons. So the quantum shot noise of the lasers kills us. And that's no way you can go beyond this. I'm not going to tell you where that limit is, but some few kilohertz, maybe at the moment. In between, it looks fine. So you're going to have some effective thing like this, which is the, in every detail, correct advanced LIGO noise curve. Right? As long as I don't put any numbers on it and can scale these axes as I want, it has to be perfect, right? And what you see is that for this drawing, which is again technically absolutely accurate for 170817, there's some band here where maybe we could detect it. Okay? And we did. So starting from the end, if we're interested in oscillations and seismology, you would expect that when 2 stars crash together, there's be some sloshing about, some dynamics, right? You'd expect that some of that was really nonlinear simulation territory. But maybe after a while, it settles down and oscillates a bit more gently. So there should be a seismology problem over here, right? And in fact, numerical simulations suggest that it's a very, very robust feature in every neutron star merger simulation that shows you what people call peak frequencies. And they are just the oscillations of this remnant. And that's a way of figuring out what the merger remnant is up to. So if it forms a neutron star-like object that's heavier and lives for some time before it perhaps collapses to a black hole, it should vibrate in some sense. So it's a seismology problem. Okay. Now over here, at some point, the stars are really far apart. You could just as well think of them as point masses. Nobody cares. But as they get closer, the fact that they have some size, finite size, comes into play. So this guy here starts raising a tide on this one, and this one responds by raising a tide over here. That tide, at least when they're far apart, is a linear perturbation problem. I put this star in the gravitational potential of this guy, and I work out the perturbations and vice versa. And then I say, well, let's get the perturbations act on one another in some hierarchy, and I just ignore that. So the tide, at least initially, is a perturbation problem. So I should be able to deal with that by hand. And we're going to, as I said, we're going to try to do that, at least get a picture. So over here, you raise a tide, which is a small perturbation, so it's a linear problem. And then at some point here, it becomes nonlinear, all sorts of things break, but, you know, and you need nonlinear simulations. But anyway, okay. So this is my introduction to the introduction. The main picture of this was to say, look, there's many good reasons. At least I tell myself that, because otherwise, how could I go into the office every day and do something, right? If I told myself this is completely useless, which it may be, but who knows, then I wouldn't be able to, you know, give lectures on this. So I need to pretend that this is important, and that's what we're doing. It is important because detections of supernova oscillations will tell us about the supernova mechanism, which is not fully understood. Will tell us about the formation of neutron stars, a problem we really can't probe in any other way, because the supernova core is opaque, right? We can't see through all the junk that is thrown out by the explosion. I think it is true, like Bernard Schutz, one of the discoverers of this mechanism, once told me, I blame him if it's not true, but it is true, that a detection of an oscillation of a neutron star driven unstable, emitting gravitational waves caused by an instability driven by gravitational waves would be one of the most fundamental observational discoveries we can make with gravitational waves. Because it's kind of a circular mechanism, and you can start probing not just how big the star is, but what the internal viscosity is and things like that, things we have no handle on at all. Okay? And then finally, we know that this is happening because we already have constraints on some aspects of the tide from 1708-17. Even though there were no detection, we have constraints on the tide. And we know also, because this is so accurate, you can see that there will probably never be just take this and move it up or down. It's very unlikely that we will detect with the LIGO curve, something like this, the actual merger. But the plans to build a next generation of detectors, Cosmic Explorer, Einstein telescopes in the 2030s, when people like us are going to be obsolete and you guys are going to be in charge, says, we are going after this because we can do this problem. So in the next 10 years or so, we need to take this problem from the drawing board, from the kind of simulations we can do today, kind of perturbation calculations we can do today, to the real thing. And I'm afraid that's not going to be my job, because I'm old and tired. It's yours. So you need to grab it and do it. And you have 10 years, maybe. Although you don't. Because the science case for these instruments has to be nailed down in something like the next 3 years. And that's my job. Right? And then you can take over. So I'll just tell you what you have to do, and then you do it. It's not going to work like that. Okay. So, now then, what do I need to do? I wrote that already, so let's keep it going. So I want to work out the seismology properties of neutron stars. Is that an easy problem or a hard problem? I think it's both. Okay? The fundamental things are really easy. They were known since at least Lord Kelvin in the 1800s. He calculated for the first time what we call the fundamental mode of a star, although he didn't know it, but he did. And that's why people sometimes call it the Kelvin mode. Okay? We're going to do that tomorrow. But then the problem is neutron stars are basically the definition of what we mean by extreme physics. Okay? So density is way beyond 10 to the 14, 10 to the 15 grams per cubic centimeter, which is when the nuclei start touching. You squeeze things together, and that means we're in a territory that we can't really probe in the laboratory. Okay? Some neutron stars have very strong magnetic fields. Magnetars can go up to something like nearly 10 to the 15 Gauss, which is many orders of magnitude stronger than, say, the magnetic field of the sun. So this is an area where QED comes into play. Things get quite nasty. Okay? Neutron stars are hot. In a neutron star merger, the temperature we see in numerical simulations ramps up to, in some cases, close to 100 MeV. Now, that means an MeV is about 10 to the 10 Kelvin. So this is hot, okay? This is as hot as the matter created in the Large Hadron Collider. So we have extreme temperature, but a mature neutron star, this kind of guys that came together in 1708, 17, so over here, it's really hot. Over here, the temperature is maybe something like 10 to the 7, 10 to the 6 Kelvin. So this is 6 orders of magnitude colder. And then you can ask, what happens if you cool matter down? Well, you know, take water, you cool it down, what happens? It freezes, right? So you know that the state of matter can change. Or if you cool helium down, helium-4, you get a superfluid. So you start worrying about low temperature physics. So these extremes, high and low, strong and weak and so on, is something we need to worry about because it impacts on the physics and it will have an effect on the problem we're trying to solve. Okay. So what do I need to do? Well, it's very dense. So you just take this, you work out something like some dimensionless number, mass compactness, mass per radius, and then put in the units. Today, I might put in units because I want to be, you know, the units might disappear as we go along in a true relativist fashion, you know. But what I'm doing today is want to contrast relativity with Newtonian physics. Okay? So therefore, some C's are going to appear probably in the wrong place because, you know, that's the way it is. So this is about 0.1, 0.2. So relativistic effects, general relativistic effects could be 15, 20%. And you need to decide if you care about 15, 20%. I don't much, but you know, but an observer cares a lot about that. Okay? And so you want to clearly make precision observations, you need to beat this. So So it's going to have to be goodbye, Isaac Newton. Hello, Albert Einstein. There's no alternative. In fact, this is an absolute necessity for a reason that many people, I think, don't really understand, but it's really simple. So the energy in a fluid, which is what we're going to be talking about, looks a bit like this. Let's call it epsilon for now. You have the mass density, so the number of particles and how much they weigh in isolation. And then something like c squared plus some other thing, let's call it internal energy. So this mass density is internal energy. So this is just how many particles do you have and how much do they weigh? Bung them all together and add them up. This is saying, in a little box of this matter, stuff goes on, it jiggles about, things happen, there's heat, there's all sorts of things, right? Internal energy. Okay. Now, if I think about what is the Newtonian limit of this, well, that's just c squared goes to infinity, right? Because in Newtonian theory, the speed of light is instantaneous, right? There's no light, but the propagation is instantaneous. So I have to get that limit by letting this is completely irrelevant. Okay. I'm only interested in mass. We're going to see that when we write down the fluid equations in a while. But this means that when I try to describe the actual matter properties which are here, I lose this piece. This piece is not small. Okay. And that means that if I build stars, for some given, say, central density, mass density or something, the radius I get is completely wrong. I mean, it's so wrong, it's not even funny. If I use a real physics matter description in the Newtonian model for stars, it's totally wrong. Right? And so Newtonian theory is actually useless for neutron stars. But we're going to use it anyway, because it allows us to understand the fluid dynamics. The fluid dynamics has the same degrees of freedom. We can learn about it, but we have to be careful. We shouldn't trust the numbers. Okay? We can do the calculations, and we are going to do that, but we should never, ever trust the numbers. We need to do a full relativistic calculation if we want the real answer. Sometimes that's easy, sometimes that's not easy. I'll go try to tell you why. Okay. So the illustration from over here is we've got to understand what happens if we have an object that requires all the four fundamental forces of nature. We need gravity, because we are having some object that's held together by gravity. We need electromagnetism, because the star has got a magnetic field. We need the strong interaction, because we're talking about neutron stars. So the strong interaction tells you that you can't have neutron stars, in the sense that stars only made of neutrons. You have to have some protons and electrons. So the strong interaction tells us how many protons and electrons do you need for each neutron, what we call the lepton fraction, how many electrons per neutron, or neutron and proton. Okay? Then we need the weak interaction, because the weak interaction that has to do with nuclear reactions emitting neutrinos tells us the rate at which the star gets older, how it cools. Okay? And it tells us over here the rate at which we lose energy through radiation. So we need all the four fundamental forces. There's no way of avoiding that. Okay? They might play a restricted role in different parts of the problem, but we need all of them. No way out. And unfortunately, there are many I did the counting yesterday, right? 9, I think I came up with states of matter represented by a neutron star. Right, you know the ancient philosophers, they had 4 elements, right? Earth, air, water, and fire. We have them, we have solids. The outer part of a neutron star is an elastic crust, it freezes. So we have a solid, we have liquids, because the core and maybe a thin ocean on top is liquid. We have gases, because outside the star there's an electron-positron plasma, which is effectively a gas of electrons and positrons. And we have fire, although you have to go a little bit, to extrapolate the meaning of fire a little bit, because we have plasmas where either the ions in the outer layers of the star squeeze out some electrons in some mixture, or again in the exterior, the electron-positron plasma is effectively some temperature-dependent object you can equate with fire. Then we have things like temperature-dependent cold temperature, low temperature physics. We have superfluid neutrons below something like 100 million Kelvin. So mature neutron stars should have superfluids. We have superconducting protons below something like 1,000 million Kelvin. So the protons should be superconducting. We have, if you squeeze hard enough, the density goes up. We might squeeze the quarks out of the neutrons and protons and get a quark gluon plasma. That's a state of matter, if you want, which may be color superconducting, which is a state of matter. You see, this is going crazy. And you're thinking, why did I come to this lecture? There is no way we're going to understand any of this. And that's probably true. We're not going to understand much of this because it's too hard, okay? So at this point, you're thinking, okay, look, I'm going to go now because I need an early lunch. Thank you. This problem is too hard. Okay? There is no single person on this planet. I'm saying that I'm probably insulting someone somewhere, you know, but I think there's no single person on this planet that can deal with all this physics at the level that we need and put it into the kind of simulations, models we need to model this, okay? This is teamwork. We need to talk to people that know the relevant things. We need to talk to nuclear physics experts so they can tell us. We need to talk to people that work in QCD. We need to talk to perhaps plasma physics people, right? We need to talk to people. It's important. You will not do this in isolation. You need to talk to people. Figure out what they know and steal it. Oh, borrow it, use it. Work with them. That's what you should do. Collaborate. Okay? Yes, please. It's coming, yeah. It should, but it typically does not. So I'm coming to that. I'm hoping to actually get to something, not just talking, but yeah, it's coming soon. I'm trying to build up to exactly that question. What we have and what we don't have. Oops. Okay, so now then, it's too hard. So either we give up, but you know, that's not what we do. So what can we possibly do? Well, let's strip this down. What is the simplest problem that we can actually do? Right? Well, let's go back and learn from history. I like this. I like going back and seeing what did people do before, because I tend to find that people were much smarter before. People like, well, Chandrasekhar, you know, sorry, I'm not going to compare myself or us to him any day of the week. We're not in the same galaxy, right? People that worked on problems before, done a lot of good work, and we can learn from that. So I talked about Lord Kelvin. He did the first calculation of some of these things, but what did he do? Well, he took a ball of fluid, right, and worked out how it oscillates. Then there's been a huge amount of work on this problem because of the Earth, ocean waves, right? There's a lot of work on observing and measuring and calculating ocean waves, so shallow water problems. This is fluid dynamics. So maybe that's where we should start. So maybe we can use fluid dynamics as some sort of canvas, as these great scientific artists we are, on top of which we paint the models, right? It gives us a framework. Right? And does it make sense? Well, it does make sense, because clearly all this stuff, in some sense, is a fluid problem. It has to be, just like the problem of ocean waves has to be a fluid problem, because there's no way I'm going to keep track of the 10 to the 52 baryons that are in the neutron star, right? I tried to set up a calculation of keeping track with maybe a Hamiltonian prescription, which you will be able to do, and then you can tell me about it, right? So I'm going to track 10 to the 52 baryons with my Hamiltonian prescription on a computer. That's my plan. This is not a good plan, because it's not going to happen. So I need some effective description, and the fluid comes to mind because everything around it, everything is fluid, right? Even the table is in a sense a fluid, because I bet if we leave it long enough, it will flow out of here. But you know, glass is a fluid, kind of, because it droops a little bit if you wait long enough. And so with a little bit of a liberal sort of extension of reality, everything is a fluid, most things in reality. Right? We breathe, the gas is kind of a fluid. So fluid dynamics. We need to understand fluid dynamics, and then we can see what we can do. And so we're going to spend a little bit of time on this. But the first thing I'd like to ask you, it comes back to your question, is fluid dynamics. But fluid dynamics is not just, you know, one thing here. Water is simplistically just, you know, molecules floating around, one single molecule, right? But blood, sorry to go there, blood is a fluid, right? But blood is not a simple fluid. Blood is a terribly complicated, not only do you not want to see it, but it's a terribly complicated fluid. It's a mixture, red blood cells, white blood cells, plasma. It has varying properties, viscosity properties, depending on how thick, you know, the blood vessels are. So it flows differently in big blood vessels compared to small ones. It's called a non-Newtonian fluid. It's terrible. Trying to solve problems for blood is like almost as hard as neutron star. Okay? So the first thing we can ask, okay, this is fine. And then you can have things like plasmas, but clearly you need charge currents. Some things need to flow. So for a neutron star, okay, so I've got fluids, but how many fluids do I need? You might not appreciate what this question means, but we'll see. Okay, so let's do a simple counting. Okay? What can possibly flow in a neutron star? Okay? So there has to be a sense of, you know, bulk flow. Something is that there's a wave like this, right? So otherwise, I can't really think of fluid at all. But then, relative to this, things can sort of move, right? So let's go to my list. What can move? Well, temperature, so heat can flow, right? So I have to somehow represent how heat flows. That's kind of a fluid problem. I wrote magnetic fields, but magnetic fields are sustained by charge currents. Charges have to flow, right? And then, if a matter becomes superfluid, so helium, if you cool it down, is one fluid, just helium atoms. But if you cool it down, it becomes superfluid. It's described by two fluids. The famous two-fluid model for superfluids. So in this case, the superfluid neutrons, say, can flow relative to the rest. Okay, now I'll go 4. I'm going to stop at 4, but I could go on. I could say quark-gluon plasmas, color superconductivity, some other things, okay? But you can see that even if I use fluid dynamics as my benchmark, this is getting difficult conceptually, right? So I don't have to track 10 to the 52 baryons, but I might have to keep track of 4 fluids, and I need to understand in what sense heat is a fluid, things like that. Okay, that's almost philosophy. Okay, so this is too hard for me on a Monday. I'll think about if I can do it later. The good news is that the mathematics for doing this kind of thing in general relativity exists. It's kind of an actually put an exclamation mark and sell that to schools, right? Good news, maths is okay. And then kids all around the world are going to be amazed by my deep wisdom. And then they're going to become a hate character for all the younger generations, something like that. So the mathematics for multi-fluid descriptions is fairly well developed, thanks to work of many great people, including Brandon Carter, who really explained how this should be done. Now, I have written a living review on this myself. It's 260 pages long or something like that. It's a lot of wasted time reading it. But it sets out how within the Lagrangian prescription, so a variational approach, you can derive the fluid dynamics and how you can extend that to as many fluid components as you like. So this is possible. But the problem is the applications are not so easy. Or less good, maybe, not bad. So the problem is that now these different components can interact in different ways, and you need to keep track of all the options, and it gets a bit messy. Fluid dynamics can be messy, and that's just life. So I don't want to go in this direction now. It's premature. But I wanted you to know about it because you need to understand that when we start doing calculations this afternoon, whatever, this is the starting point. The end point is somewhere here. The end point is being able to put this on the computer to ultimately do this. And we are quite far away from this, right? In all honesty. Partly because the problem is too expensive. I don't have a big enough computer, and I'm not smart enough to simplify the problem so it fits on the computer. That's life. But that can change. So let's start coming to your question about the equation of state and things like that. So let's go back. Still got 2 boards. I have to stop when I get to the end, right? I talked a lot about physics. I'm sure that was not very inspirational or anything, but it had to be done. So let's talk about fluid dynamics in general relativity. I think if you've all done a first course on general relativity, you've probably seen the perfect fluid. Is that true? How many people have not? Okay, so no one wants to admit that they haven't. So you all have, right? You're all experts. Then you can go for an early lunch. Again. So what do we do in general relativity? Well, so we do something like this, right? We pick a fluid element there, and then we work out its world lines, how it moves in space-time. Each world line has a tangent vector. We call that U. Now I need to decide my convention. Okay, I'm going to use Roman letters starting with A for space-time, just to mess up everything that happened this morning. And then I'm going to use I, J, and K for three-dimensional spatial indices. That will mess you up, okay? So that's what I'm going to do. Okay, so UA, A is 0 to 3. Okay. Now, it doesn't matter. You can use whatever convention you want, Greek or so on. It doesn't matter. So we can work this out because we know how this is defined. And we know this is going to be important later, of course, that with the metric GAB, the four velocity, which is defined here, is defined with units as minus c squared. Right? And then later, of course, I'm going to lose the c's and the g's and whatnot. I'm going to lose everything. Probably. So what is this? Well, this is effectively a 1+3 decomposition, right, of space-time. If I have a fluid, I can use the fluid to split because I can put clocks on this guy and that gives me time. And then I have a description that covers all of space. Of course, only in a region where I have a fluid, right? So this is very similar to that Hamiltonian idea, right? That you get the vibration of space-time where you invent the time, the rest is orthogonal to that. The mathematics says that 1+3 is equal to 3+1, but in relativity, that's not true. So we need to be careful now. Because when we do numerical simulations, we don't keep track of fluid elements like this. Instead, we set it's a foliation of space-time with a normal vector that gives us a time-like object. We split it in 3 and 1. And that's different. And that means that the physics that lives here and here is naturally represented here in the vibration, and I keep track of where the fluid is, right? It is not naturally represented here because these are not the same. Okay? In a numerical simulation, it's actually one of the hardest things in numerical relativity, is to go between what you get from your simulation back to the real physics and then back again. And this is where the equation of state comes in, where you need to know what the physics is in this little box that you're trying to describe. Okay? It's a hard step. You write in your numerical simulation so that it works. That's over here. But each step, kind of, you have to go back and ask, well, what does the fluid do? Because you're trying to keep track of a real fluid. And that's really hard. Okay, so we know what we want to do. We want to solve the Einstein field equations, right? We know that the Einstein tensor, again with units, is something like 8 pi g over c to the 4th, and the stress energy tensor, right? That's your problem. The equations are there. Go and solve them. Shouldn't be too hard. You know it's hard. But we know more So how does the argument for fluid dynamics go in relativity? It goes a bit like this. Well, we have this, but this is too hard for me. So instead, I know that the Bianchi identities tell me that the Einstein tensor is divergence-free, right? That's a typical thing that you see in the relativity course. You probably work this out, right? Everyone does. Because when you derive the Einstein field equations, this is a key step. You define the Riemann tensor, define the Ricci tensor, work out the Bianchi identities, and show that this is true, right? Because this is how you get that the combination of Ricci, tensor, and scalar is what it has to be. Okay? And then what we tend to do is say, well, if this is true, then this means that these are just numbers, I don't care about them. So this means that this has to be true. The stress energy tensor has to be divergence free. Okay, that's the next step. And now, magically, we have 4 equations. Right? And they've got to do with energy and stress and momentum. So we think that, okay, these 4 equations are somehow related to energy and momentum conservation and stuff. Right? So then we get excited and we say, well, you know, I'm trying to describe fluid dynamics. What's fluid dynamics? Well, that's effectively energy and momentum conservation for matter, right? And now I have some equations that supposedly are energy and momentum conservation. So surely these must be the same, right? So we say, okay, look, here are the equations of motion for fluids, right? And then we get super excited and we say, ah, look at this. And then I'm going to we invent this T, it's a perfect fluid. Did I write that? No, I didn't. So we invent a TAB, and we don't have that many ingredients, but we have 2. We got the 4 velocity and the metric. So we can write down an object that has 4 velocity and metric, straight up. So that we start off with an energy, and then we construct this so that the projection of TAB on the 4 velocity twice is the energy, right? And then we introduce another bit that we call the pressure. And now we need this to be orthogonal to the 4 velocity, because otherwise it counts in here and we didn't want that. So we need to put in a projection. And the projection is the usual TAB plus UA UB, so that projection on UB 0, something like that. Okay? You've all seen this, right? Absolutely everyone has seen this, I'm sure. I've seen this. Now here's a question. Over here, I wrote down an object and I called it epsilon, and I called it energy. Okay? Were you awake when I did that? Okay, that's fine. Over here, I wrote down an epsilon and I called it energy, right? Are these 2 things the same? The same symbol, but maybe that was just a sleight of hand. Are they the same? Are there 2 answers? No, 3 answers. Yes, no, or maybe. It's an energy density. That's an energy density too. It's an energy density, but is it this energy density? That's not obvious, okay? Because this is on the small scale inside this fluid element. This is on a big scale. So there could be other stuff that's hiding in here that's not counted in there. But if I worry about that, I get stuck. So we typically assume that this is the same and this is the fluid pressure, and that this fluid pressure is given by an equation of state that we understand. Okay? But this is a map between the small physics and the fluid that is built on an assumption that they are the same. And it's important not to get lost in the fact that just because we use the same symbols doesn't mean that the physical quantities have to be the same. Otherwise, this would be really easy, right? Let's call the two things you want to be equal, call them the same, and then move on. So that doesn't work. So we have to be careful. Remember, this is an identification. Right? It doesn't have to be true. In reality, in fluids, there's probably a lot of other stuff sitting in here that's not in there. Turbulence, for example, is turbulent energy. It's going to sit in here, but it's not in there. So one has to be a little bit careful. But this is okay, because ultimately, the fluid model is just a bit of phenomenology, which I can't spell. Can't spell it at all, which is really impressive. Okay. So we need to keep this in mind, that effectively what I've done, I've taken a bit of matter and I've averaged over a bunch of particles to get some single thermodynamic number out. I called it the energy. And then I've written down a piece of mathematics that, remember, how is this motivated? It's motivated actually by two things. Number one is motivated by the fact that mathematically, in the vibration, I only have two objects. I have the four velocity and the metric, and there's only one combination I can build that has two indices, like the stress and intensity needs. Use the metric and two velocities. That's all I can do. So it has to look like this, right? But this is all I've got. But this is a really, really dangerous thing to do, right? Because I'm talking about real physics. So why should the real physics just have these 2 degrees of freedom? In fact, the general stress energy tensor, as you'll see in one of the examples we constructed for this afternoon, can have other things like stresses and things. In electromagnetism, you've got the electromagnetic field. If the heat flows, you've got the heat flux. So there's more than this, okay? But this is only a part of the story. And then we identify this with the real physics because we want to make progress, okay? And you can ask, well, what happens here? Well, I know that if I take the, so is it completely crazy? Well, we know that Einstein's field equations are built to reduce to Newtonian gravity, right? We know that. So we know, actually, no, it's not quite that. And again, you've seen this, I'm sure, in the derivation of the Einstein field equations, right? Where you build up and say, okay, I've got the Einstein tensor now, what should I put in the stress energy tensor? What is this, okay? Where you say, okay, I know it has to reduce to Newtonian gravity. In the weak field limit, I need something like the UA, UB, TAB, which is epsilon. I need that to reduce to rho c squared in the Newtonian limit. Right? And then you know that out of Einstein's field equations comes Newton's law of gravity, right? So this identification is not crazy at all. It makes total sense because we know it goes back to this. But remember, the fluid also has this. So in the Newtonian limit, we lose that. I said that already. And that's not part of this story. So the relativity equations could contain more in the sort of stress part, which doesn't sit here. And the question is, should we be worried about this? I don't know. Sometimes. So what happens now? Do I have a little bit of space? So we can work this out. We can just plow on and work this out. So let's do that. We've got the four velocities solved. We're going to do this and then sort of wrap it up with that, I think. So if we project along the four velocity, take this equation, multiply it with the four velocity UB, it's just going to be a number. It's going to be a scalar equation. It's going to look like this. This is actually in your exercise for later. So I'm just going to sketch the result. One way of writing it will be like this. So U alpha, UA, partial A on epsilon. So it's a time derivative along the flow plus P plus epsilon divergence of U. So there's a four divergence, there's a proper covariant derivative that has to vanish. It's an energy conservation law, right? And the momentum conservation, you've seen this, I'm sure, is P plus epsilon C squared down there, I think. And then the directional derivative of the flow, the UA grad A UB, that's a plus, and the projection on B, C, say, partial CP. This is what comes out, the standard textbook fluid dynamics equation, right? So, now finally, your question. Let's do the function counting. How many variables? How many equations? 1, 2, 3, 4, 5, 6, minus 1, 5. So 5 equations. Right? Right? Oh, sorry. Yes, you're right. Talking and writing, not the strength. 5 variables, 4 equations, right? So this is not job done. We need more. We need one more. So we need the equation of state. Okay? So and this is where we hide all the physics. And then, as proper relativists, we make this someone else's problem. So give this to me, and I can do the rest, okay? So this is typically some relation. This is where all the physics goes. And now I have about 10 minutes to talk about all the physics. Lucky me. Okay. So what is this going to be? So this, I'm going to take this to be some epsilon of something, whatever the variables are. Okay. Now I ran out of space, so I should stop, but I'm not going to because I'm insisting on this. Okay, so let's get rid of this. Okay, now we have to decide how difficult do we want to make this? Not very, right? We want to make this manageable. So let's do that. Let's say let's take a 2-parameter model. Okay? N is the number of particles per unit volume, so a number density. S is the same, but for entropy. So this is now thermodynamics because I'm talking about entropy. Don't worry about it. Just think of that as a variable. Then it's easy to see. We know that clearly you can do a variation on this. So the variation change with n holding s fixed plus the change with s holding n fixed. Yes, right? And then because this is going to get messy, we're going to give these some names. So the number change in, if I change the number of particles holding the entropy fixed, this is called the chemical potential. And this guy here is called temperature. Okay. So now we have a model with two parameters only. And then I go to my big book on thermodynamics, statistical physics. Sorry, I hope you have one. I should have written one. I could have solved it now, but it would have been great. But it probably wouldn't have been a very good book. So then we need one more thing. We need a thermodynamic relation called the Gibbs relation or fundamental relation or whatever, with many names. Basically says that pressure plus energy is the product of, again, actually, if you want to talk about conjugate variables and so on, this comes from a flux, this comes from a momentum, this is effectively a Hamiltonian picture of thermodynamics, but I'm not going to go there. If I'd known about this morning, I might have done it, you know, but. So here's the relation, okay? And now it's easy to work out with this definition, this relation, that the change in pressure has to be just m d mu plus s dt. And this is going to be important, okay? Because now I can reduce the number of variables by one. I have one new identity, I can reduce the number of variables by one. Great, I'm done, right? 4 equations, now 4 variables, but at the cost of having to understand a bit of thermodynamics. Great. It's fantastic, right? Apart from we're not done. But I hope the next bit is easy. So here is a problem for you. There is a pesky law of physics that says that baryons are conserved, right? So in this model I've just written down, there should be a conservation equation like this, right? Number of particles move along is conserved. So now I seem to have the same number of variables, but one equation too many. So I'm back in trouble. I just fixed the problem, but now I'm back in trouble. So this is one of the things you're going to be trying to prove this afternoon, that you're not in trouble. So why are we not in trouble? Well, we can write out what this equation will look like easily, and then we'll fix it. So this is going to look like something like this, I guess, exactly like this. There are no geodesics because you're in a fluid. So you cannot. Okay, now I have two equations. We're going to resolve this conundrum and then we're going to have lunch. I have this. And I'm asking, does this cause me trouble? Because I also have this. The answer to the question is on the board. Okay? And the easiest way to see it is let's just suppose that this is cold, so we have no entropy. Let's make it a little bit easier, because otherwise I need to take an extra step and I don't have time. Let's just kill this piece. Okay? If I kill this piece because it's cold, then I kill this piece. Now I know a relationship between pressure and density. I also know a relationship over here between energy and number density, right? So then I know the epsilon is mu dn. From the Gibbs relation, I know that P plus epsilon is n mu, right? And you know, you saw it, right? And you see that now I can plug in over there, wherever I have the epsilon, plug this in, and this equation comes out. Or multiply this equation by mu, right? Take a mu times this. And this second bit is a mu n, that's P plus epsilon. This piece is mu dn, but that's dn. Just turn these guys into derivatives, you're done. Okay? So the thermodynamics saves the day. And so this tells you that if you want to do fluid dynamics, you have to understand the thermodynamics, which is fine because you need to understand what goes into your calculation anyway. Right? You need to understand what's the matter made of, and that is ultimately a nuclear physics thermodynamics problem. And that tells you, I think, why the equation of state or matter is so central to everything that's got coming when you talk about neutron stars, okay? Two reasons. We needed to be able to calculate anything, otherwise the problem is not well posed. So the mathematical reason. And then the physics reason, because this is where we're going to put in all the stuff, okay? So now I cheated, right? I said, this is really easy. I only have one particle species and heat. We want more. So tomorrow we're going to be a bit more bold and put in some extra species here and see how we can use the physics to simplify the problem. Okay. So the other thing that's going to happen this afternoon is, well, you're going to be asked to work out basically textbook exercise, these kinds of problems for yourselves, just to think about it, okay? Warm up your computational muscle, and anyway, have a nice relaxing kind of couple of hours after doing some proper calculations in the first workshop problem class, right? So that should be okay. The other problem is a little bit messier, and that is to connect the relativity with the Newtonian fluid equations. So take the Newtonian limit. It's actually not that hard, because all you need to do is know what the energy looks like, plug it into this kind of equation and take the limit of C becoming large. The problem is, it is a degenerate limit because the metric will diverge. So you need to be a little bit careful. There's a place in the calculation where you lose any powers of C squared. That's what you should try to pay attention to. But it's just an exercise because when we do calculations tomorrow, I'm not going to do it in relativity. I'm going to do the modes in Newtonian gravity. This is easier. But for now, I'm done, I'm bang on time, and you've probably well cooked already. So now you've earned your lunch. Thank you very much.
So are there any questions? So I am assuming we are considering this to be a conservative system, right?
Yes, for now.
Yeah, so because I am confused about like what if we are including the nonlinearities of Einstein's equation?
Okay,
Like how that will reflect on the fluid side.
okay.
Thank you.
So that's a really good question. At the moment, I'm aiming towards linear perturbations, right? Non-linear aspects will make life very difficult in general. Two reasons. In, non-linear GR is hard, right? This numerical simulation territory. And secondly, non-linear fluid dynamics with turbulence is also hard, right? So we've got two problems that are hard, and there's probably more than 2 times 2. That's difficult, right? So at the very end, on Friday or something, I might talk a little bit about where things are in terms of simulations trying to do exactly that, do the nonlinear physics. But right now, it's a little bit early. Right?
So how these numerical simulations counter the gravitational waves part?
Oh,
Like,
no, the
that is the
gravitational waves.
dissipating-
So, no, gravitational waves are totally contained here, right? It's just that
Oh, I see, I see. Okay.
the gravitational waves sit here and need to solve also for the space-time.
Yeah.
Okay,
I see.
I just wrote down the fluids because I'm aiming at fluid dynamics now. But the full problem, where we're getting to, towards the end, Thursday, Friday, is also the metric. Okay, so that's the other big difference. Newtonian theory, you have no metrics and nothing, just the gravitational potential. In general relativity, you have to worry about what the metric does. Okay.
Thank you.
Anyone else? Okay, so if not,
I
let
think they
us
want
thank,
lunch now.
let's thank Professor Andersson again.
Thank you.
So now break for lunch.